Okay, I want to say a little bit more about limits today before we move on to continuity. And the thing I want to talk about is what happens when we say a limit goes off to infinity or diverges to infinity or to negative infinity. So we often write, for example, limit of, say, for 2 sub n goes to infinity equals infinity. Well, this equality, it's kind of abusive notation because, I mean, limits can equal numbers, but infinity is not a number. It's not a value, it's not a quantity, it's sort of an idea, right? So what do we mean that a limit equals infinity? It's really abusive notation. We don't actually equal infinity. It's sort of a defined statement as a whole, right? The whole thing is defined, not just equality there. So our definition for a sequence to diverge to infinity, we say the limit of a sub n as n goes to infinity equals infinity. I'm going to leave a little space there. We'll go with a plus sign for now because I'm going to talk about what it means to go to negative infinity as well. We say that this goes to positive infinity if eventually the sequence is unbounded. So what does it mean to be unbounded? It means that for any bound that we try to put on it, so we'll take a bound in the reals, there exists a point where the sequence is always bigger than that bound. So that point would be there exists n in the natural numbers such that if n is bigger than n, then a sub n is bigger than b. Right? If I go far enough out in the sequence, my numbers in the sequence are bigger than the bound I tried to put on it. And that was true for any bound that we tried to put on it. Okay? So that just means that this thing just keeps getting bigger and bigger, and once it gets big, it stays big. Okay? So what would I want to do if I wanted to put negative values in here? So if I try to put a negative infinity in, well, the bounds can stay in the reals, right? This checks out okay. And I still want to go far enough out in the sequence, that checks out okay. And I want the things to be far out in the sequence. The thing that changes is this changes to a sub n is less than the bound. Right? These bounds, these could be positive or negative. Right? And so when I'm dealing with going off towards positive infinity, the ones that really matter here are the positive ones. When I'm going to negative infinity, the ones that really matter are the negative bounds. So I'm changing the bound which side I want to be on. So for the positive ones, we're here. For the negative ones, we're here. Okay, and those are our two definitions for what it means for a limit of a sequence to go to infinity or negative infinity. Let's see an example. Let's prove this example right here. So the limit as n goes to infinity of 2 to the n equals infinity. So proof. So what we have to do to use this definition, I have to take any bound that I can think of. So let b be a real number. And I have to say how far out in the sequence I need to go for that real number to be below the rest of the sequence. So, well, there's kind of two cases here. if b is less than or equal to 0, I really don't have to do anything because our 2 to the n's are never less than or equal to 0, right? It's an exponential function. It's always positive. So if b is less than or equal to 0, take n equal to 1, then a sub n is bigger than 0 is bigger than or equal to b for all n bigger than 1. Okay. Otherwise, take n bigger than the ceiling of the log base 2 of b. Why do I want to do that? And what do I mean by the ceiling? The ceiling is the next highest integer. So the ceiling of pi, for example, would be 4. It's the next integer that I would get to. Okay. So if I do this, then I probably want a capital N here. Sorry. Then if n is bigger than n, we have n is bigger than log 2 of b, which now I'll just exponentiate both sides. Exponential functions are monotonic, which tells me 2 to the n is bigger than b, which we wanted. Okay. So if I want to be beyond b, I have to go out log 2 of b spots in the sequence, and then the sequence will always be bigger than b.